Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference, Algorithms Learning. How do artificial brains learn optimization math? It corresponds to one of several short conferences, in which the advances of HI research are presented, on the topic of artificial brains and decision-making artificial intelligence. Lecture edited by Jesus Velasquez Bermudez. The list of short introductory lectures to decision-making artificial intelligence are presented in the picture. How do human brains learn? By Donald Hebb. Neurons that fire together, wire together. Donald Olding Hebb, July 22, 1904, August 20, 1985, was a Canadian psychologist who was influential in neuropsychology, where he sought to understand how the function of neurons contributed to psychological processes such as learning. He is best known for his theory of Hebbian learning, which he introduced in his classic work, The Organization of Behavior, 1949. Hebb has been described as the father of neuropsychology and neural networks. His views on learning described behavior and thought in terms of brain function, explaining cognitive processes in terms of connections between neuron assemblies. The central concept of Hebb's theory is summed up in the phrase, cells that fire together, wire together. According to this idea, when an A neuron is repeatedly involved in the activation of a B neuron, the synapses between them are strengthened. This principle suggests that the concurrence of neural activity is the basis for learning and memory. Synaptic strengthening: when a presynaptic neuron and a postsynaptic neuron are activated simultaneously, the connections between them are strengthened. Activity-dependent plasticity: the efficiency of synaptic connections is not static but can be modified as a function of neuronal activity. This plasticity is essential for adaptive learning and memory. Then, learning is not about new cells, but about new connections. Because of the creation of new and more efficient connections in the brain. Experience induces synaptic change facilitates pattern competition, activity, not synaptic change, is sufficient for memory cognition. We define augmented artificial intelligence, AAI, as the creation of artificial intelligence from the neuroscience of human intelligence, integrated with the mathematical laws of smart physical systems. The creator of the human brain conceived it as the integration of three main organs, or systems: neocortex, hypothalamus and hippocampus. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. Emphasizing that HI is not an expert in neuroscience, its interpretation of the functioning of the brain is presented. The cerebral cortex stores all the connectivity of the neural networks that make up the brain. The hypothalamus is the organ that ensures the proper functioning of the human being. The connectivity of neurons in the cortex determines how the hypothalamus should function. The hippocampus is responsible for managing memory, which interacts with the hypothalamus, to determine the actions that the human being will perform, that is, decisions. Artificial entrepreneurial brains are based on these hypotheses. Artificial cortex. The neocortex contains millions of neurons that communicate with each other, to capture the world that occurs around the human being. The connectivity of these neurons does not occur based on a dense network, that connects all neurons to each other. Connectivity is based on a sparse network, which can be assimilated to a sparse array. Neuroscientific studies associate the network of neurons of the cerebral cortex in layers, and in columns, connected in an organized hierarchical way. In mathematical models, it is common to use a matrix that relates columns with variables, and equations with rows. The normal thing is that these matrices are sparse, structurally similar to that of the human cortex. Therefore, the learning process of an artificial brain involves increasing the number of connections that are mapped into the artificial cortex. This section is based on the paper "Why Does the Neocortex Have Layers and Columns? A Theory of Learning the 3D Structure of the World." Neocortical regions are composed of columns and layers that performs robust object learning and recognition. Columns integrate their changing inputs over time to learn complete models of observed objects. Lateral connections across columns allow the network to more rapidly infer objects, based on the partial knowledge of adjacent columns. Because columns integrate input over time and space, the network learns models of complex objects that extend well beyond the receptive field of individual cells. The image presents the hierarchical distribution of neurons in the neocortex, joining brain, neocortical columns, simple neurons and ion channels. This is the starting point of the Hawkins model. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. This is the fundamental representation of the 3D connectivity of neurons in the neocortex. This structure has the same characteristics as those generated when a monolithic model is divided and decomposed into an atomized model, to process it in parallel. Artificial hypothalamus. The hypothalamus must coordinate all the processes that the human being carries out. The artificial hypothalamus must connect the multiple mathematical models, algorithms, that are part of the artificial brain, exchanging information between them to obtain a common goal, mathematically an objective function. This activity must be autonomous, permanent, and based on distributed processing. The artificial hypothalamus emulates the human hypothalamus as a computer-distributed processor that solves multiple problems, representing the holistic model of an organization. This process can be called autonomous real-time distributed optimization. The optimization methodologies to be used are selected by the artificial hypothalamus. This diagram shows a three-level structure. Result of partitioning and decomposition of a system, using a simple methodology of large-scale optimization, like Bender's theory or Lagrangian relaxation. The diagram presents the hierarchical structure of decomposition and partition of an oil company. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex. The representation is based on atoms, or neurons, which is normally a tuple composed of time and an organization asset, where the assets are connected forming a network, in which each of them represents a dynamic vision of the neuron. In 1983, Tony Van Roy created the cross-decomposition approach to solving large-scale optimization problems, based on partitioning and decomposition techniques, and mixing different types of methodologies, such as Lagrangian relaxation and Bender's theory. Cross-decomposition, developed by Van Roy, makes it possible to establish complex optimization processes, in which multiple methodologies are used on a large scale. This allows the problems to be adjusted to the most convenient methodology for the solution of each subproblem. This implies a universal conversation between multiple algorithms, built with different methodologies. It also frees the decomposed problem from bidimensional hierarchical tree-like structures, enabling horizontal communications between subproblems. From the point of view of multi-layer structures, cross-decomposition results in the exchange of information between multiple layers, of different columns, like the actual structure of the human neocortex. As in the human cortex, lateral connections between columns allow the network to solve problems more quickly, based on partial knowledge of adjacent columns. Cross-decomposition can be said to be a smarter scheme, due to the creation of new and more efficient connections in the artificial brain. To handle the concept of mathematical intelligence, Hai developed the concepts of mathematical artificial neural nets, MANN, which complement the concepts of artificial neural networks, ANN. Within a nervous system, a neuron is an electrically excitable cell that fires electrical signals called action potentials through a neural network. The neuron is the main component of nervous tissue in all animals. Neurons communicate with other cells through synapses, specialized connections that commonly use minute amounts of chemical neurotransmitters, to pass the electrical signal from the presynaptic neuron to the target cell, across the synaptic gap. Neurons are highly specialized for the processing and transmission of cellular signals. Given their diversity of functions performed in different parts of the nervous system, there is a wide variety in their shape, size, and electrochemical properties. For instance, the soma of a neuron can vary from 4 to 100 micrometers in diameter. An artificial neuron is a mathematical function conceived as a model of biological neurons. Artificial neurons are elementary units in an artificial neural network. The artificial neuron receives one or more inputs, representing excitatory postsynaptic potentials and inhibitory postsynaptic potentials at neural dendrites, and sums them to produce an output, or activation, representing a neuron's action potential which is transmitted along its axon. Usually each input is separately weighted, and the sum is passed through a nonlinear function known as an activation function, or transfer function. The transfer functions usually have a sigmoid shape, but they may also take the form of other nonlinear functions, piecewise linear functions, or step functions. They are also often monotonically increasing, continuous, differentiable, and bounded. Transfer functions usually have a sigmoid shape, but they can also take the form of other nonlinear functions, piecewise linear functions, or step functions. They also tend to be monotonically increasing, continuous, differentiable, and bounded. An artificial neural net is based on a collection of connected artificial neurons, which loosely model the neurons of a biological brain. Each connection, like the synapses in a biological brain, can transmit a signal to other neurons. An artificial neuron receives signals, then processes them, and can send to neurons connected to it. The signal at a connection is a real number, and the output of each neuron is computed by some nonlinear function of the sum of its inputs. The connections are called edges. Neurons and edges typically have a weight that adjusts as learning proceeds. The weight increases or decreases the strength of the signal at a connection. Neurons may have a threshold such that a signal is sent only if the aggregate signal crosses the threshold. Defining parameters and topology is a combination of empirical work and scientific work, but there is no mathematical theory that must be respected. The algorithmic process is cyclical, and its convergence is based on the minimization of errors. The precision and representativeness of the process are directly proportional to the number of neurons that can be handled, which is why the development of associated technologies is exponentially enhanced, with the enhancement of computer technologies. Hai developed a theory for building networks of artificial neurons specially built to integrate the artificial brain and fit into the structures of the artificial cortex. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets. This new type of neuron will be called mathematical artificial neuron. Its name was derived from the fact that the neuron is built, based on mathematical models that represent a system, and that it does contains logical or intuitive elements. The mathematical artificial neuron is a mathematical model, presumably of optimization, which results from the partitioning and decomposition of a monolithic problem into an atomized model, following the mathematical laws of large-scale mathematical modeling. Two mathematical artificial neurons communicate with each other, forming a network of mathematical artificial neurons. Communication occurs in two directions between the two neurons. The communication protocol between the two neurons is defined by mathematical laws developed to solve atomized problems. The modeler can choose the protocol, but not the communication process, which for optimization is based on the scientific laws of duality theory, and for equilibrium problems in mathematical programming with equilibrium constraints, PEC, methodologies. A mathematical neuron represents a robot, which can communicate with another robot, autonomously, since it knows the mathematical rules that it must respect. This is what happens in the human brain, where autonomic systems communicate with each other to make decisions. The mathematical artificial neuron is the technological evolution from the biological neuron, typical of mental intelligence, to the neurons necessary to represent mathematical intelligence, which until now are not produced by the human being. The mathematical artificial neuron is the technological evolution from the biological neuron, typical of mental intelligence, to the neurons necessary to represent mathematical intelligence, which until now are not produced by the human being. Like all mathematics, theory is cadent, And for those of us who already work in high complexity mathematical modeling, it is the logical step we must take. It's just widening the look, and thinking a little outside the box. The mathematical artificial neuron is a mathematical superstructure, representing a complete system. A mathematical artificial neuron network can be a neuron of a larger mathematical artificial neuron network. This law of transitivity is typical of large-scale modeling. A large-scale system can be represented by a mathematical artificial neuron, and covers multiple subsystems, where each of them can be represented by a mathematical artificial neuron. Using large-scale methodologies, the mathematical artificial neuron can be divided into two, or more, mathematical artificial neurons, forming a mathematical network of artificial neurons. This process can be repeated, until the smallest mathematical artificial neurons, the atoms of the system, are obtained. Artificial hippocampus, a mathematical model's expert system. Hippocampus store the experience, and the knowledge acquired over time in the human brain. The learning process of the human being is concretized in memory, which accumulates information to face each new situation using the accumulation of knowledge that has been made up to that moment. This information is stored in the hippocampus where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last days, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them, remember. It could be said that, to support decision-making, the artificial hippocampus stores historical information related to the models formulated and that work correctly, and the runs made with a certain model, in such a way to be able to use this information in new runs. The first case has already been analyzed throughout this presentation. The information is stored in the hippocampus where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last days, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them, remember. Algorithms that learn during the solution process. While mathematical models on digital computers, and the data storage disks, date back many years, more than 60 years, and despite the Industrial Revolution 4.0, how to run a model, it does not seem to have evolved. The normal process is: the model is thinking monolithically. A high-performance solver is selected to solve the problem, and the results are post-processed, and the results of the models are stored, with administrative purposes. Usually, in the next run, the model starts from scratch, ignoring the past, that is, it has no memory. In some cases, it is heated from a starting point provided by the last run, presumably the last optimal solution, or a point that ensures feasibility. However, an artificial hippocampus, designed for the artificial brain, can take advantage of a lot of information produced within a run, and during the history of all runs. Two examples will be briefly presented: handling of Bender's theory, and generation of convex Hull. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. Artificial brains are based on multi-problem mathematical models, the solution of which must be addressed with large-scale optimization methodologies. As an example, we will analyze the construction of an artificial hippocampus using Bender's partition theory. Benders divides the model of a system into two: a coordination problem and a dependent problem. To solve the model, a conversation is established in the two problems. The solution of the model involves a conversation between the two math problems, or agents. The coordinator, over y, variables controlled by the board of directors, and the subproblem, over x, variables that are controlled by the production manager, and that depend on the decisions of the board of directors. In its original form, Bender's algorithm involves a sequential conversation between the coordination problem and the slave problem. In non-mathematical terms, the board of directors sends a set of technical decisions to the production manager to assess their impact, that is, the marginal costs and benefits, for all resources, which are the economic indicators of the board's decisions. With this information, the board analyzes the optimality of its decisions and, if not, sends a new proposal. The process involves the partition of the monolithic model into two smaller problems, the coordinator and the subproblem. This will reduce memory and processing time requirements. This division does not produce knowledge to solve the model. It simply produces two problems, which only together can solve the model. To solve the problem, Bender's devised an algorithm in which the coordinator captures the information provided by the subproblem, through constraints, called cutting planes, in red, in such a way that, under certain mathematical conditions, the algorithm converges to the optimal solution. At the time of convergence, the cutting planes represent everything that the coordinator learned from the subproblem, and the subproblem is not necessary. If only certain parameters change, the next time the issue runs, the subproblem may not be necessary. Like any optimization problem, this one has a matrix formulation that Hai has associated with the artificial cortex. The problem is divided into the coordinator, psi-bt, and the slave, SPBT, each with its own connection network in the artificial cortex. Splitting the problem is splitting its matrices. When starting the optimization process, there are no cutting planes and therefore this part of the problem does not exist in the artificial cortex. Psi-bt includes two types of cuts that limit the feasibility zone of Y, in other words, indicate decisions that cannot be made by the CEO. The first type, that we call optimality cutting planes because the cut eliminates values of board decisions that can't be optimal every time the slave problem is solved, until the optimum, or until a nearby feasible solution, a cut of this type is generated. The second type, the feasibility cutting planes restricts the feasible zone of board decisions to maintain feasible solutions in the production problem. Every time the slave problem produces an unfeasible solution, a cut of this type is generated. The second type, the feasibility cutting planes restricts the feasible zone of board decisions to maintain feasible solutions in the production problem. Every time the slave problem produces an unfeasible solution, a cut of this type is generated. The coordinator's solution implies a learning process in the algorithm, which is configured with the minimal connectivity. As iterations occur, the number of connections in the artificial cortex increases, which corresponds to the learning of the algorithm, that is part of the artificial brain. If the dual variables of the subproblem of each iteration have been stored in the artificial hippocampus, when the process stops, and starts again, including the previous cutting planes, everything will be faster in the second run, implying that the brain has learned from one run to the next. For example, a basic artificial hippocampus can be constructed using Bender's partition theory, which can be interpreted as: the general problem is divided into two complementary subproblems, an experimenter, that makes decisions in real, or in simulated, environments, and that send the results to the higher level, and an information manager, that stores the results, sent as primal and dual variables. When it is required to make a real decision, or to perform an experiment, the information manager processes the stored data to determine two zones with respect to decisions, a desirable zone and a non-desirable, or utopian, zone. Mathematically, this is done by generating cutting planes and incorporating them as part of the information to be processed. The experimenter receives the information from the manager, makes decisions, and sends the results to the manager. The speed with which this loop is made can be that of an algorithm, that does not stop until it finds the optimal solution, or that of a human who makes decisions step by step. The first non-optimal zone that contain values of the decision variables, that must be discarded because they cannot be optimum. From a human point of view, it contains decisions that should not be taken because there are better. The second non-feasible zone, that contains values of the decision variables, that must be discarded because they cannot be feasible. From a human point of view, it contains decisions that cannot be taken because they are impossible. Decisions not included in the two zones determine the area of rationally desirable and possible decisions. Algorithms learning. MBP, multi-level Bender's partition. GSDDP. Generalized stochastic dual dynamic programming. From the concepts of partition and decomposition, it is possible to multiply the connections represented in the artificial cortex. Therefore, aiming to have algorithms that can solve atomized problems to the maximum, it is a way of giving the artificial brain the capacity to learn. A clear example is the cross-decomposition. HI has initially developed sequential algorithms, and subsequently parallel algorithms, based on variations and extensions of large-scale optimization methodologies. Nowadays HI is oriented to support the development and growth of algorithms to support artificial brains. Some of them are described below. Since the programming of the first version of Optex, the so-called multi-level Bender's decomposition theory was implemented, which generalizes the Bender's theory to multiple levels of partitioning and decomposition. Multi-level theory is based on the application of standard Bender's theory, in which the problem is divided into two. Bender's theory is applied again to the subproblem, and so on until it reaches the lower level of the system, that is, the atom of the system. This diagram shows a three-level structure. Result of partitioning and decomposition of a system, using multi-level Bender's decomposition. GDDP, Generalized Dual Dynamic Programming. And, in 1991, Jesus Velasquez Bermudez, founder and chief scientific officer of HI, developed the first version of what would end up being called GSDDP, Generalized Stochastic Dual Dynamic Programming. They are variations of Bender's partition theory, which were formally published in 2002. GSDDP includes risk management, from a scientific approach, using the conditional value at risk. The general structure of GDDP is two-level, and its goal is to reach the smallest atom from the time point of view, that is a mathematical neuron for each period of the planning horizon. This diagram shows a multi-level structure that can be solved using the combination of MBP and GDDP, producing atoms, mathematical neurons associated with pairs of time and random scenarios. The image can be associated with the vertical connectivity of an artificial brain to face the design problem of a global multi-business organization. The following table and image resume the study of behavior of GSDDP for a stochastic mixed linear economic electricity dispatch. The decrease in the solution time per scenario, when increase the number of scenarios, is a measure of the learning capacity of the GSDDP. Artificial hippocampus. Storing the history of runs. Following the principles developed by Bender's, it is possible to build an artificial hippocampus that remain active and useful beyond the duration of a run of a computer model. To do this, the cuts generated in each run must be stored in such a way as that they may be used later. This implies a coordination work, since it cannot be guaranteed that the information as it is produced can be reprocessed later. Optex, as an expert system, stores the cuts of one run to be used in the next, which will produce new cuts. HI is researching in the creation of methodologies to generate new rules that fit the dynamic variation of the parameters that affect the models. While all the mathematical support is solid, there is no theory that can indicate which cutting planes should be selected when restarting the model. Problem that becomes big when the size of the database grows. For this reason, it is considered necessary to develop tools, based on traditional artificial intelligence, artificial neural nets, to help the management of the hippocampus database. The idea is that for very large problems, the selection process will include an ANN. This is one of HI's research projects. HI is working on the use of convolutional neural networks to select the cutting planes to be extracted from the memory of the artificial hippocampus, to incorporate them into the mathematical problem whose solution algorithm is in a continuous learning process. Convolutional neural networks, CNNs, were designed for the processing of structured data, such as images, videos, and time series. They are based on the concept of convolution, which allows the network to learn important patterns and features in the input and output data. CNNs are widely used in pattern recognition tasks. An example of a CNN aimed at recognizing images of numbers written freehand is presented. In this case, the result is a discrete indicator associated with the number read. HNN assimilates the arrays of cutting planes that are in the memory of the hippocampus, and the arrays of the parameters of the problems to an image. This is true because images on a computer are stored in arrays of pixels. Both CNNs and the visual cortex have a hierarchical structure, with the simple features extracted in the first layers and the more complex features integrated into deeper layers. This allows for increasingly sophisticated representations of visual inputs. A CNN applies a set of convolutional filters to the input image, each filter triggering different features of the image, allowing for faster and more effective training. This filter concept can be extended to the output matrices, those of the cutting planes. Now, instead of images, we have input and output matrices, of cut planes, and exogenous parameters from past experiences, which are related to the input parameters of the new problem to be solved. One application of this approach is Imitator, a CNN that allows pre-trained models to recognize the conditions of the carbon mixture and the characteristics of the resulting carbon for a thermoelectric plant. As iterations occur, the number of connections in the artificial cortex increases, which corresponds to the learning of the algorithm, that is part of the artificial brain. If the dual variables of the subproblem of each iteration have been stored in the artificial hippocampus, when the process stops, and starts again, including the previous cutting planes, everything will be faster in the second run, implying that the brain has learned from one run to the next. The interested reader can consult the white paper. Artificial Hippocampus: The Energy of the Artificial Brain. The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers, will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. An artificial intelligence without dynamic memory and automatic learning capacity, it can't be smart. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.